Hello and welcome to this video. What I'm going to do is I'm going to explain the astrometric method and the radial velocity method of finding exoplanets. So I'm going to start with the astrometric method because it is the more basic of the two. The astrometric method, or astrometry for short, consists of observing stars to see if they wobble. So why would they wobble? Well, a star, as you can see in that animation there, the star is the larger object near the center, and the planet is orbiting the star. But notice that the star is also moving. It's moving in a tiny circle. So the star and the planet are bound together gravitationally, and they are actually both orbiting around the center of mass of the two objects. So what happens is the star appears to wobble in the sky. When we look for exoplanets, we actually are not looking for the planet itself. We're looking for its effect on the star. And the effect that that exoplanet has on the star that you're seeing in the animation is that it causes that particular star to wobble in the sky. It's making a tiny circle. So what an astronomer would see over a long period of time is they would see the star drifting back and forth in the sky. All stars have a type of proper motion. That is because the stars are moving, they're orbiting the center of the galaxy, just like the sun is orbiting the center of the galaxy. So over time, it does make a motion against the rest of the background stars, so in relation to each other. But generally, scientists will see it make a small wobble. So what if we were to look at the sun and Jupiter from a distance of about 33 light years away? A light year is the distance that light travels in a year. So we would have to move quite a distance away. But if we could do that and we could observe the sun and the effect that Jupiter has on the sun, we would see the sun making out a wobble pattern like that shown in the image. Okay, in this image, you'll see that there's a series of years. So this would be the position of the sun on 1990. And then we go around this wobble. Here is where the sun would be in the year 2000. Here is 2005. Here is 2010. 2015, and 2020. So this is the wobble that we would see if we could get 33 light years away. Or if there was an advanced civilization looking at us from 33 light years away, this is what they would see, and they might actually be hypothesizing, are there planets around the sun? All right, so there are some positives and negatives to this way of searching for exoplanets. One positive is that one telescope can search many stars at a time. That's because they can take a series of photographs and then they can compare the photographs to each other, the positions of the stars. And if they see a star has wobbled out of position, that gives them the idea that there might be a planet there. Now, there are some negatives to this. One is this method doesn't work for very far away stars. It's very difficult to see the motion the further away the star is. It's also very difficult to detect terrestrial planets. Those are planets like the sun, like the Earth, excuse me, that are very tiny. And because they're tiny in comparison to the size of the star, they wouldn't cause that star to wobble very much. And right now, our technology isn't sensitive enough to see a large movement that would be caused by a planet the size of our Earth. Also, the process is very slow. An astronomer needs to observe several orbits of the star, of the planet and the star together. They need to observe several orbits to verify that their findings are correct. They aren't going to just see one wobble and then say, hey, I found a planet. They're going to have to do this multiple times. They're going to take their initial data, they're going to verify their data, they're going to take more data, they're going to verify their data, and they're going to have to watch several orbits. Now, if the planet takes 365 days, like the Earth does, to go around its star, then it's going to take maybe 5 years before they say, hey, I've got a planet. But if the planet orbits the star in, say, 4 days, they could probably verify that planet in a couple of months. So it does depend on how far away the planet is orbiting from its star. All right, the next method I'm going to go over is the radial velocity method. And it is an extension of the astrometry method. Now, this method uses slight changes in the star's velocity and the concept of redshift and blueshift using the Doppler method. So what is that about? Well, remember from a previous lesson that the Doppler effect is the change in frequency of a wave as perceived by the observer. And you've experienced this most likely when it comes to sound waves. The animation that's showing is a sound wave, and as the object is moving towards us, the wavelengths in front of the object are being compressed together. And as the object moves away from the observer, the wavelengths behind the object are being stretched out. So if we were hearing a horn, for instance, as a car was driving by us, we would hear a change in pitch from a high frequency to a much lower frequency. So how this relates to astronomy and light waves is the change in pitch is seen as a change in color. So when the wavelengths are compressed as an object is moving towards us, they are blue shifted. And as the object is moving away from us, the waves are stretched out and the object is red shifted. So the way that looks is compressed waves are smaller wavelengths. That's the blue end of the spectrum. Here are the wavelengths in nanometers, 400 nanometers on the blue end of the spectrum. On the red end of the spectrum, when the wavelengths are stretched out, the wavelengths are larger at 700 nanometers. And the way that would look is a dark line spectrum, which are the bars that represent elements that are present in that particular star. The dark lines represent the elements, as I said. And when those dark lines are shifted towards the red end of the spectrum, the wavelengths are longer and the object is moving away from us. And on the other hand, when the wavelengths are on the blue end of the spectrum, the wavelengths are being compressed because the object is moving towards us and the spectrum is shifted towards that blue end. So here's some stationary spectrograms, for you to see. The top one is a spectrogram that's in a laboratory setting. So the object is not moving. So here, all of the lines in the second one are shifted in the direction of the red end. So that's a red shift. The object is moving away from us. The wavelengths are being stretched out. On the bottom one, the wavelengths are shifted towards the blue end of the spectrum. So that object is moving towards us. The wavelengths are compressed. Here's another one showing the same thing. It's just reversed. So here's our laboratory standard. And here these lines are shifted to the red end, that object's moving away from us. And here on the blue end, it's blue shifted. So this object is moving towards us. So what does that have to do with finding a planet? Well, I'm going to stop screen share. I will come back to this animation and I'm going to put you on me so I can do a little demonstration. So I'm going to use two objects. This object will represent the star and this object will represent a planet. So remember the astrometry method where the two objects are they're balanced gravitationally. They have a center of gravity. And the center of gravity will cause both objects to orbit around a center of mass. So sometimes when you think of an orbiting planet, you think it's going around the star and the star is stationary like this. But what's actually happening is they're both orbiting around a center of mass. So what happens is when scientists are observing stars and looking for exoplanets, what they see is the star doing this. They do not see the planet at all. So what's happening is, regarding the red shift and the blue shift, as the object is moving towards you, it is blue shifted, and as the object moves away from you, it's red shift. So what the scientists will pick up is a change in the red shift, blue shift. They're going to see something like this. They're going to see blue shift, red shift, blue shift, red shift, blue shift, red shift. It's blue shift as it's moving towards the observer, and it's red shift as it's moving away from the observer. So it's blue shift, red shift, blue shift, red shift, and that helps them detect the planet. All right, so I'm going to go back to screen share here and back on our animation. So what we have here now, this is, you're going to have to think about this as a little differently. This is our star and our planet, and the observer's down here at the bottom of the screen. So at this point, when the planet comes around this way, it's moving towards the observer at the bottom of the screen. So it's blue shifted. And then when it's over here, it's going away from the bottom of the screen, so it's red shifted. So that's what they would be picking up. They would be picking up the blue shift, red shift, blue shift, red shift. As the planet is orbiting the star, it causes the star, the light from the star, to be blue shifted and red shifted. All right, so what are the pros and cons of this method? The pros are that the radial velocity method can be used on faraway stars. So our equipment has been fine-tuned enough to be able to pick up red shifts and blue shifts of faraway stars. Using the astrometry method by itself, that doesn't work. But with the red shift and blue shift, the Doppler effect, we can pick up faraway stars. A con is that it can only observe one star at a time. So with the astrometry method, you can observe hundreds of stars at one time. So what they do is, with the astrometry method, they'll find the stars with the wobble, and then they'll spend some time looking at those stars individually with the radial velocity method. So they aren't typically going to look for planets using the radial velocity method initially. They'll start with the astrometry method. It's difficult to detect terrestrial planets because the terrestrial planets are causing the star to wobble very little. So it's hard to pick it up. And just like the other method, the process is slow. It needs to take multiple orbits before the scientists will say and announce, yes, I have found an exoplanet. So I hope that helps you in answering the questions of the lab related to the radial velocity method.